It has to do with curiosity. It has to do with people wondering what makes something do something. And then to discover that if you try to get answers, that they're related to each other. That things that make the wind make the waves, and the motion of water is like the motion of air, is like the motion of sand. The fact that things have common features turns out more and more universal. What we're looking for is how everything works, and how everything is, what makes everything work. And what happens first in the history is we discover the things that are on the face of it obvious. And then gradually we ask more questions, and then we dig in a little deeper to things that we can just make. We need to do a little more complicated experiment to find out about it.
Fabulous. I like that a lot. Like, crop circles in secret are actually luminous at night. Here we discover them as the nebula part, and we present the name of our guest. And here we are, live.
Hey y'all, I'm Sunny Shell, and tonight Bre and I are talking with Ethan Siegel. So sit back, buckle up, and let's get to the sunny spot on Skeptic Haven. Hey!
Hey, good evening. How you doing?
I am doing good, and you're looking lovely as usual.
As are you, my dear. I'm
Well, thank you so much.
Yes, because I've never shared the screen with this gentleman before, but I know you guys are like old friends.
Oh, I adore him. I get all just fangirly and giggly and silly. So I'm so glad that tonight we are speaking with Ethan, and I want to thank everyone for spending your Thursday evening with us. So, Ethan, thank you for joining us.
Yeah, it's my pleasure to be here. Thanks for having me back, Sunny. We've had a good time before, and I know we will do so again. And Bre, it's our first time together. I hope after today you leave and you're like, you know what? I'm gonna be stoked the next time I see that face.
I'm excited. Yes, let's learn some space stuff. That's what I want to learn. I want to learn about the Big Bang, because that's when I was reading about you. That's what they said you were all about. Is that true?
Well, they do call me a Big Bang cosmologist, but that's sort of like saying that, like, oh, well, that's the foundation that you build your life upon, so that's what you study. And yeah, it is the foundation that I built it on, but that's sort of like saying, like, oh, are you one of those Darwinian biologists or one of those non-Darwinian biologists? Well, honey, we're all Darwinian biologists if we're biologists. We just, what do we build upon that?
Mm-hmm. Well, I got a really good question for you that I want to start the night off with.
Oh, right out of the gate. Sure.
Right out of the gate.
Right
yes, I want to know, what are the newest discoveries about exoplanets? And do you think we'll ever find signs of life?
Okay. So just recently, less than a year ago, we found our 5,000th exoplanet. So that's a big, big threshold to cross, right? Back in 1990, not that long ago, I mean, pretty long ago, I guess, but not all that long ago, we didn't know for sure if there were planets around stars other than our own. We only knew of the planets for certain in our own solar system. Now, today, we've gone through about 10,000 exoplanet candidates, which is to say we saw about 10,000 things where, oh, we see how this star is varying. Maybe we're watching how it moves and it looks like it's moving towards us and then away from us and then towards us and then away from us. And that can be because there's a planet orbiting it. And we can't really detect that side-to-side motion, but we can detect the towards and away motion. So if we see something that moves towards and away, it's a good candidate for a planet around it. But other things can cause that. So you have to confirm. Another thing is you can say, oh, well, if you're looking at a star, every once in a while, a planet might pass in front of it and block a little bit of its light. So if you see that periodically it gets dimmer and then returns to normal and then gets dimmer, you see that magic 3 times. 3 times is, now we've got a good planetary candidate, but you have to confirm it, right? A lot of things can mimic that. Binary stars in particular are big confounders of this, which is why it's exciting to say 5,000 confirmed. Like, no, we found all those imposters out there, and we sent them over to, like, oh, the binary star astronomers can have these, and the other astronomers can have those imposters. It's a flux dipping star, not an exoplanetary system. But we've got 5,000 plus, 55069 the last time I checked, bona fide discovered exoplanets. More and more, by the way, are coming out of the same data set when we apply machine learning techniques to them. So that's also a kind of a new discovery, is when you look at the data with our traditional methods where we have a template and we fit the template to the data, that uncovers most of them. But every once in a while, you can have a computer teach itself, ooh, well, why don't you come up with what a different, right? You say, make a mock simulation of all the types of exoplanetary systems that can exist, plus show yourself what it would look like in the data, and then take this real data and say, are there maybe some planets that we missed in there? And yeah, we did that with a big data set, and like 70 new planets showed up. So that's some cool stuff. Now, we're not at the point in our technology that we can detect signs of life on them today. If you want to detect what we call biosignatures, or that the more conservative astronomers call biohints, then what you need to do is say, well, look, I want to watch this planet, and I want to take the light from this planet and take a spectrum of it. Because if I get a spectrum of it, now I can start seeing what types of atoms and molecules are present in its atmosphere. And then I can start seeing, oh, well, what am I seeing? Are these levels constant over time, or do they change with the seasons? We want to be able to do direct imaging of these exoplanets so that we can see, oh, do they have clouds? Do they have continents and oceans that change when they rotate as the planet revolves with the seasons? Does it do something like Earth, where it change colors, where the ice caps advance and retreat at the poles, where the continents green and brown with the seasons? If we start to see something like that, we're going to know for sure. Now, everyone's super antsy, right? I want this now. I want this today. And here you're telling me, oh, we don't have the technology today. Well, good news for those of you who aren't about to die tomorrow is we're making progress towards this. Right now in space, we have observatories like Hubble and the James Webb Space Telescope, but not the next NASA flagship mission, which is the Nancy Grace Roman Observatory, but the one after that. That's been chosen, and it's called Habitable Worlds Observatory. And its big science goal is it's going to take anywhere from maybe 20 to up to maybe 100 of the nearest candidate exoplanet systems for life, and it's going to directly image these worlds. And that's going to give us that data that we need. There's a chance we'll even get there first, because right now the largest ground-based optical telescopes are about 10 to 12 meters in diameter. But we are currently building 2 30-meter class telescopes. And, you know, size isn't everything in astronomy, but it sure does help. So you build your telescope 3 times the diameter, and you can gather 9 times the amount of light and get 3 times the amount of resolution. So there's a really good chance that sometime in the 2030s, we might see, hey, you know, and look, you're probably going to see it many times where it's like, astronomers say they found an inhabited planet. And then you're going to read Ethan and he's going to be like, no, hold your horses. You did not do that. But maybe by the 6th or 7th time someone makes that claim, they'll actually have the data to back it up. So I do think we'll find signs of life. I look at how Earth is. We have all the right ingredients for life, and we had successful life. Now, plenty of other planets are going to have these ingredients and not have life. But also, I bet you there are plenty of planets very different from Earth that have the ingredients and that have life too. So we're trying not to close our minds off to any of the possibilities that are out there, but we're making sure we're going to look. Also, I should mention there are two other approaches people have to looking for life. One is to just hop directly to planets in our solar system, or worlds or moons or asteroids or whatever, and look, hey, was there ever life on this? If we sent humans to Mars and said, hey, here's a drill, go drill a core and go take your Mars lab and analyze this soil in the Mars lab, you could see, are there microfossils? Did we have evidence of past life in here? Is there even dormant life still living there, just waiting to be reanimated when you poke it with some liquid water? And the other way is we're also listening for signals of extraterrestrial intelligence. For a long time, that was the main way we were looking for alien life, was hoping there are intelligent aliens out there trying to communicate with us using radio waves. And if we just, Ellie Arroway it up, we can maybe hear them. But that's only one of three ways. We're looking at worlds in our own solar system, at exoplanets, hoping to take direct images and measure their atmospheres, and looking for signs of extraterrestrial intelligence. Now, my bet, if you ask me to bet on which one of those is going to bear fruit first, I'd bet on the exoplanet one. But all three avenues are valuable, and there's a reason we do the science. Just like in the sports world, there's a reason they play the games, is you don't know who's going to win until the game is over. So let's have fun playing the game.
I have a question real quick about something you had mentioned there. When you said about the exoplanets looking for it to planets like going brown to green, are there other star systems where we look for the planet to go to different colors based on the light?
Oh, we would look for any colors. The problem is our telescopes today are only good enough to get like Neptune-sized planets and take direct images of them.
No.
That's great if you're someone who's like, I think Neptune is the best. But if you think a planet like Earth is the best, you want to image planets that are maybe rocky, with maybe thin atmospheres instead of thick atmospheres that would crush anything on the surface. So that's why you got to wait for either the 30-meter class of ground-based telescopes or that Habitable Worlds Observatory that's coming. That's the NASA Astrophysics flagship mission after the Nancy Grace Roman Observatory.
So it's all plotted out. Wow.
So before we go on,
you got to plan this science decades in advance, because it's very ambitious stuff, and you need the backing of the entire community to make it happen, right? Because you know how things are. You get like 1,000 different scientists, and they're like, I want to look for life like this. And someone's like, no, you're an idiot. I want to look for life like this. And then someone has to come in and be like, okay, children, like, I'm going to be the grown-up. Here's our instrument suite that we're going to build. Here's the general all-purpose observatory we're going to build, but it's optimized to do this and this and this and this. And here's our primary science goal, and we're going to make sure that all of the best ideas are getting incorporated into this observatory. That part alone takes years.
That's keeping science competitive like that makes it interesting, though, because like you got the same thing with like teams. We're gonna resurrect the mammoth. Oh yeah, we're gonna resurrect the thylacine. We're gonna see who does that first. Who brings back the first extinct animal? Just the same.
No, I see you've got a radioactive Jurassic Park creature behind you.
Yeah.
So I have a quick question from someone in our chat. Really quickly, I wanted to highlight it. What's a theoretical astronomer involved? Does Ethan champion and introduce new science to the field, or does he work on existing hypotheses and theories?
So this is a good question, right? There are multiple different types of theoretical astrophysicists, right? Sometimes people focus on theory development and say, well, we have this theory and I want to explore more and more consequences that we haven't yet observed of this theory. And that was like my favorite thing to do, is to take what we already knew, like, oh, well, one of the things I did was say, well, look, we think that every galaxy is full of dark matter. but it shouldn't be this smooth distribution of dark matter. It should also be clumpy internally. It should have what we call substructure within it, where, yeah, overall, on average, we have a big halo that's denser in the middle and gets less dense as you move away from the center. But you should also have little clumps of dark matter moving through it. And we also have these almost perfect natural clocks in the universe called pulsars, right? They stand over here and they spin and they spin and they spin on their axes. Some of them spin very fast. Some of them spin hundreds of times a second, where you measure their period in milliseconds. And like geniuses, we call these millisecond pulsars. So you have a millisecond pulsar and it spins and it spins. And every time its axis passes by your eye, you get a blip from it. You get a signal from it. So it rotates and boom and boom and boom, and you can hear it bip, 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 bip every time it goes over. The really fast ones, like brrr, right? It keeps going like that. Well, if you get a clump of dark matter that passes between you and the pulsar, it's going to delay the signals. And then when the clump leaves, the signals are going to come back to normal speed. So I had this idea back in 2006 or 7 or so, and I wrote up a paper, and yeah, this is it. This is a way to look for dark matter and tell what type of dark matter it is by using this pulsar timing and looking for variations in the timing of the arrival of the pulses to see, do we have a clump of mass that's moving through, and can we tell what its mass profile is and its density profile and measure it? So that's one example of what theoretical astrophysicists do. But theoretical astrophysicists also do simulations. They do cosmic simulations to say, well, if I put these conditions into place, what do I expect will happen? And then I can compare my model and my simulations with the observations. And theoretical astrophysicists also say, well, this is what happens in the standard picture. What if I tweaked it? What if I made a change to it? And then this other thing happened instead, or this new thing happened. What would happen? What would the consequences of that be? What would that look like? And then what do I observe, and could that explain it? So there are a lot of different aspects to being a theoretical astrophysicist. Because I'm mostly nowadays a science communicator, I ask the big question of anything I come across: what is true? Right? Because I want to make sure that we don't mix in the speculative stuff that, although it's interesting and we're considering it and we're working on it and we're looking for evidence for it, I want to make sure that what's speculative at present isn't mixed up with what we know to be true. So that speculative stuff is really important. All of that is like right on the cutting edge. Some of it's way over the cutting edge, but some of it's right on the cutting edge. But let's make sure when we're talking about any of this science stuff that we make sure we don't mix up what we're certain is true over here with what may be true, but we don't have the evidence supporting it over here. I hope that answers your question.
Sonny, you're muted, I think.
Goodness gracious, I can't believe I did that. I'm so sorry. He also went on to ask, by the bending of space-time around the pulsar because of the mass of the dark matter. I think he's talking about the...
Yeah, that was something I worked on. That was something I worked on back in the day. And yes, because mass bends space and time, that means, as you know, if you have a signal and you have a clump of mass that passes in between you and where the signal is coming from, as that mass arrives, it's going to bend the space. So you might see a spatial shift in where that signal from the pulsar appears to come from. You might get a time delay in the arrival of the pulses that appears when it moves in, and then you're going to get a reverse of that delay. It's going to catch up again when the mass moves away. So yes, both space and time are bent by mass and all forms of energy. So that would be a thing that some people are looking for and trying to measure when it comes to pulsar timing in the search for dark matter.
Okay, that makes perfect sense to me. Well, I shouldn't say perfect sense. It makes sense to me.
It makes
What you're talking
enough
about.
sense to you.
Yes, exactly. You had mentioned the James Webb Telescope.
Yes.
Can you tell us what discoveries we have made recently with the telescope?
Oh, someone needs to fix that caption. JWST.
JWST. Let me see if I can do that. I'm going to do that.
So the James Webb Space Telescope is the largest, most powerful light-based space telescope we've ever launched. Hubble is a tin can in low Earth orbit, about 2.4 meters in diameter. James Webb Space Telescope is 1.5 million kilometers away from Earth. It's 4 times as distant as the moon, and it has a custom 5-layer sun shield on it. All of the instruments on JWST face away from the sun because that sun shield passively cools down the telescope to about 40 Kelvin. That's 40 degrees above absolute zero, or below the temperature of liquid nitrogen. So that's pretty cool. But it has a mid-infrared instrument that goes even colder. It's cryogenically cooled, I believe, with liquid helium down to 6 Kelvin. And the reason you want it to be so cold is that's the limiting factor on Hubble. Not just the size of the mirror. James Webb is 6.5 meters instead of 2.4 meters, which is awesome. But James Webb is also cold because if you've ever worn an infrared camera and you can see how your heat signature moves around, Hubble's limited with that because even with its tin can reflective coating, it's always basking in the glow and the heat of Earth, in addition to being in direct sunlight. So Hubble never gets down below about 200 Kelvin. So it can see a little bit into the infrared, and then you get what's called thermal noise, which is just the telescope itself is hot and it emits heat, and you can't see anything colder than that. But James Webb Space Telescope doesn't have that limitation. It can see, so Hubble, to give you scale, human eyes can see between 400 and 700 nanometers. Hubble can see out to about 2,000 nanometers. James Webb Space Telescope can see out to 28,000 nanometers. And because of that longer wavelength, larger aperture, and better instrument suite that it has, my favorite discovery that the James Webb Space Telescope has made is it has broken the old record for the most distant galaxy ever seen. So the James Webb Space Telescope has, with Hubble, we were able to find one galaxy that was about 400 million years after the Big Bang. Then it had like one more that was like 500 million years after the Big Bang, and maybe like 2 more within that first 650 million years. Now, with the James Webb Space Telescope, the earliest galaxy is just 320 million years after the Big Bang. We've got 5 that are before 400 million years. So we've got 5 that have all broken Hubble's old record. And we've got like maybe 20, 30, 40 within that first 650 million years.
Wow.
So James Webb Space Telescope hasn't even been doing science operations for 1 year. And it has revolutionized what we think and how we understand the earliest stars and galaxies in the universe. We also know, and this is one of the things I love, that most of what James Webb Space Telescope is seeing are actually like the biggest, brightest galaxies out there at that time. It's not even most of the galaxies. Most of the galaxies are small little rinky-dink things that are maybe only 50 or 100 light years wide at that point because they're so young and primitive. We think that's what emits the majority of the ultraviolet radiation, the ionizing radiation in the early universe. So this is really important because when the universe, you have your Big Bang, the universe expands and cools, you make neutral atoms. That's good. We need neutral atoms to make gas and stars and all of these wonderful things we like. But neutral atoms block visible light. They block the kind of light we see and that Hubble sees. So going into the infrared not only is beneficial because James Webb Space Telescope can see it, but it allows us to see these galaxies that ionize, that when they turn on the ultraviolet light from them, reionizes this intergalactic matter and makes the universe transparent to the kind of light we can see. So I would say the biggest discovery we're making with the James Webb Space Telescope on a cosmic scale is learning how the universe grew up. We are seeing, instead of just like one little baby picture of something in the universe, it's like we're getting enough snapshots that we can see how it's building and how it's growing up. It's also seeing things that, just thanks to its infrared capabilities and its instrument suite, we never knew before. For example, it went and observed what's called a dusty debris disk around a young star called Fomalhaut. Fomalhaut is, I think, the 21st brightest star in the night sky. It's also the brightest star in the sky to have one of these dusty debris disks in it. And what we found was fascinating. It looks like, yeah, it has like an inner disk that looks analogous to our own asteroid belt. Mm-hmm. And it has what we call an intermediate belt that looks a lot like our Kuiper belt, where all those comets come from out beyond Neptune. But it looks like there's a third outermore belt around it too. And that is wonderful. We weren't expecting that. We weren't expecting, oh, well, maybe other solar systems don't have two belts like an asteroid belt and the Kuiper belt. Maybe they have three belts. Do we have a third belt? Why not? What's more typical? This is new questions that come up because we discovered something cool that we weren't expecting to see. So this is always what I tell people. People always want to know, hey, Ethan, some new observatories coming out. What are we going to see? I'm only going to be able to tell you the stuff that I'm anticipating is going to be out there. Whenever you look at the universe in a fundamentally new way, you open up what's called discovery space, which means give the universe a chance to surprise you. Because when it does, you're going to learn something you never would have expected you'd wind up learning.
That's so cool.
I gotta ask about specific discoveries. Maybe it's not something fancy that's new to science, but just the images of these Wolf-Rayet stars and the formations around them. Oh my God, they're beautiful, like flowers, and yeah. Can you tell us a little bit about that?
Wolf-Rayet stars are these very, very massive, short-lived stars, right? If you're a Blade Runner fan or a pyromaniac, you might have noticed like the flame that burns twice as bright lives just half as long. For stars, the situation is way worse. If you take a star like our sun, comparable in mass, made out of the same stuff, it's going to live about 10, 12 billion years before it runs out of fuel and dies. If you double the mass of the sun and say, hey, what's a star about twice as massive as the sun? How long is that going to live? The answer is it only lives 1/8 as long. It lives about 1.5 billion years. While stars come in really massive varieties, 10, 20, 50, 100, 200. The most massive star we've ever found is 260 times the mass of the sun. And these Wolf-Rayet stars are like 50 to 100 times as massive as our sun or more. They only live for like 1 or 2 million years before dying and going supernova. So when we see these Wolf-Rayet stars, we know, oh, my dude, you are not long for this universe. Those flower shapes you see, those are its outer layers of gas that have already been blown off of the star itself, that are being ionized and illuminated by the high energy radiation coming off of the star. What James Webb Space Telescope can see is the colder atoms in there. It can see the things that have condensed to form atoms and molecules. It can see the things that have collected together to make little dust particles. So it can see a different part of this blowing off matter that cools and condenses and heats up than the optical telescopes can see. It's easy to see the hot ionized plasma things. It's much more difficult to see the cold, dusty molecules that are present there. But JWST can see it all.
When you were talking about earlier about how the James Webb Telescope can see further than we've ever seen before, as far as the earliest galaxies.
Mm-hmm. That's correct.
How long does it usually? I mean, there's got to be a point where we won't be able to see any further because there wasn't enough time for a galaxy to form. How long does it take for a galaxy to form?
This is a good question, right? What we are learning is there had been simulations that say, I don't think there should be any galaxies until like 200 to 300 million years after the Big Bang. And a lot of people didn't trust those simulations because whenever you make a simulation, you're sort of limited, right? You have a volume of the universe that you're simulating, and there's only a finite number of particles you can put into your simulation to simulate. So you wonder, oh, am I missing anything at really high resolution by running the simulation at the maximum resolution my computational power allows? Well, there was a study just earlier this year that said, hey, we took this different simulation, one that used something called an adaptive mesh, which basically means when the density gets above a certain amount, we're going to zoom in and focus more on that little part to see how things collapse. And it turns out that, look, the universe started with an average density everywhere. And like water waves on the surface of the ocean, you might get a few parts of the ocean that are a few centimeters higher or lower than average. But that's nothing compared to the ocean, which is many kilometers deep in most spots. But those little fluctuations on top are very important. The universe is born like that, with little tiny overdensities and little tiny underdensities compared to the average density. And where you have an overdense region, that's going to grow and preferentially attract matter into it. And that's where you're going to form stars and galaxies first. And those underdense regions down here, they're going to give up their matter to the more dense surroundings. So people are saying, look, if you want to know when an average density region or a slightly above average density region is going to form stars and galaxies, you can look at those coarse, low resolution simulations. But if you want to know where the first ones are going to form, you need to look for the biggest overdensities that exist, the ones that will draw matter into them the fastest and grow the fastest and make structure first. And those simulations say, look, I think we can start making stars as early as 100 to 150 million years after the Big Bang. So what the James Webb Space Telescope is doing with these earliest galaxies it's seen, and I'll preface this with so far, I fully expect the records it has now to be broken many times over, including, I'll say conservatively, I expect the current record to be broken by the end of the year.
Oh, wow.
Conservatively. Because the galaxies we're seeing already, they are big, they are massive, they are bright, and they are evolved. They already have heavy elements in them like oxygen and carbon and iron and things that you can only make inside of stars in previous generations of stars. So these early galaxies that we are seeing, they are not made out of pristine material. These are not galaxies that we're looking at the first stars because it's forming stars for the first time. These galaxies they're old. Like, for it's funny to look at a baby galaxy and be like, "You old bitch," but they are. They are. They have been around probably for 200 million years already in some form or another, and that's what we're seeing. So yeah, there is going to be a limit to how far we can see stars and galaxies, because there's going to be a limit to, at some point there weren't any stars and galaxies. But the big thing we've learned is, yes, we've seen earlier than we've ever seen, and we have not hit that limit. And I would argue that James Webb has shown us we're not even close to that limit.
So cool. I don't want to. I want Bre to ask a question, but really quickly.
I just said exciting. There was no question. Go ahead.
Okay. The reason I wanted to ask something really quickly is because James Walton, who is asking really great questions in our chat, he asked that we please ask you this. Do you concur with Sir Roger Penrose on the CCC cosmology, which I don't know what he's talking about? So can you explain?
Sure. Very briefly, there is this idea of the hot Big Bang, and the universe began with the hot Big Bang. But if you listen to my previous episode, you'll know we currently think the Big Bang is not the very beginning of the universe, but rather the aftermath of a previous epoch in the universe. That the Big Bang is this hot, dense, expanding state, right? You look at the universe today and you say, oh, it's sparse and it's expanding and cooling. So if you extrapolate back in time, then it was hotter and denser and more uniform. And maybe you can extrapolate all the way back to when it was a singularity. No, you can't do that, because we see that all these pathologies would have arisen, and the universe observationally doesn't look like a universe that would have started from a singularity that got arbitrarily hot and dense. There's a maximum temperature that it reached, and therefore you would say, oh, well, something must have happened before it was hot and dense and expanding and full of matter and radiation. The best theory that explains that is called cosmic inflation. That's a theory that was put out in the early 1980s by Alan Guth. Many people worked on predictions of it and theory development of it. And by the end of the 1980s, we had many different predictions for, look, if you take the Big Bang theory without inflation and this new version where cosmic inflation precedes and sets up the Big Bang, you can come up with separate side-by-side predictions that you can go out and test against each other. And the Big Bang says, oh, well, the universe should have reached arbitrarily high temperatures. And inflation says, no, you should only reach a maximum temperature that's like a factor of several thousand below this supposed Planck temperature. And the Big Bang says, oh, well, you should see a universe that, it has sort of random fluctuations in it, right? And, inflation says, no, you should get a particular spectrum, a Harrison-Zeldovich spectrum of adiabatic density fluctuations. And that's what we get. And you should also get a universe that exhibits these fluctuations that appear on scales larger than the cosmic horizon, larger than signals could have traveled even at the speed of light from one region to another in the Big Bang. And we see those. So the Big Bang doesn't give us that. Overall, there are 4 separate predictions that have been teased out that should be different between inflation and the Big Bang without inflation. And inflation's 4 for 4. So that's the standard picture. Now, Penrose has put out an alternative to this. He put this out in the late 2000s, and he calls it the CCC, the conformal cyclic cosmology. And he says, instead of a Big Bang or inflation, that you had a previous era of the universe that collapsed, and then it bounced, and then you get a new universe that comes out of this. Now, in Penrose's model, if it's correct, he said, oh, well, I make a new prediction that's different than either the hot Big Bang without inflation or the inflationary model. And what I predict is there will be these things in the universe that are like these concentric circles that appear that have these temperature fluctuations in them. And there should be like 20,000 of them in our observable universe. And he called them Hawking points, and he came out with an algorithm to go and look for them, and we have looked for them. Newsflash, nobody sees them except Roger Penrose. And the limits that we placed on them say, oh, instead of like 20,000, there's at most like 20 in the universe. So look, no, I don't concur with Sir Roger Penrose, and I would argue that anyone who looks at the data and compares them with the theory doesn't agree with Roger Penrose. Now, Roger is brilliant, and he made some tremendous contributions to physics about black holes, to mathematics, to general relativity, to twister theory. He has done a lot of valuable work, and the CCC isn't part of it. I predict, because this is what happens to a lot of scientists as they get older, is they come up with their own pet ideas that conflict with observation, but because they are big famous names, no one tells them, dude, this is wrong, you have to stop saying this. So he goes out and he says this, and my prediction is someday Roger Penrose will die, and the day after he dies, no one will work on the CCC anymore because it's wrong. It's observationally been shown to be wrong, and it's not a very useful idea. So I'm sorry to anyone who is a Roger Penrose fan. I'm a Roger Penrose fan, but I am not a CCC fan. And if the data were to come in differently, I would be. If you're someone who cares about what the universe says when you ask it questions about itself, you should always subject it to that critical test. No matter how beautiful your idea is, if it disagrees with what the universe tells you about itself, it isn't worth very much from a scientific point of view.
Yep, absolutely. Bree, do you have any question before I continue on? Because I have all kinds of questions.
Go forward, yeah.
Okay. So you know that I love black holes. We've had many discussions on black holes. They're like my thing. So have we learned anything new about black holes since the James Webb Telescope was released?
You know, we have learned a few new things about black holes, but they haven't come from the James Webb Space Telescope. That's not the best tool for looking at black holes. But, you know, honestly, if I think hard about it, one thing I can tell you that the JWST has shown us about black holes is James Webb Space Telescope has multiple instruments. The big glorious images you see are mostly from what's called its near infrared camera. That's the shorter set of infrared wavelengths. But if you move to longer sets of infrared wavelengths, that's where the mid-infrared instrument takes over. And every once in a while, you'll get a mid-infrared view of a galaxy. And you will see at the center of this galaxy these six big bright spikes coming out of the center of the galaxy. When we see that, that is the signature of an active black hole that is not seen in other wavelengths of light. So the James Webb Space Telescope has shown us, including in its very first image, remember it had that early science release where it had like 5 images that were released, and one of them was of this group of galaxies called Stephan's Quintet. In one of those galaxies, you see those spikes coming out of it. And we didn't know that that galaxy had an active black hole at its core. So if you look at a mid-infrared image of a big spiral or elliptical galaxy and you see those 6 spike patterns coming out of the central bulge of the galaxy, there's an excellent chance that you are looking at an image that discovered an active supermassive black hole in the center of that galaxy.
Oh, that's so cool.
I'm wrong. You can use JWST to learn something about black holes.
That's so cool. Is that one of, I know shortly after the JWST went, you were on the show and you showed us, I think it was 5. And it seems like there was one that, if I remember right, that had those spikes in it. Do you remember if that was one of them that we looked at?
You know what? I'm just going to have to find the image and make you share it, if that works.
Absolutely. Yes, you do that, because that's that is I think it's something that would be really cool for everyone to see. And
Oh, how dare.
I think we did view
All right.
that.
I don't have a chat window to dump this in, but I'm just going to drop it in your little private chat over here. And that's a link to the mid-infrared image. And you can see up in the top of the image, if you want to share that image, this is exactly what that 6 spike pattern looks like.
Oh, that's so cool. I'm talking to Wes in the background. Are you able to cue that up, or do you need me to do that? I'm trying to figure out. I don't remember how to do that right now with a website. I'm going to see if I can try it. Oops. What did I just do with that? Okay.
I think you might be able to just hit that present button at the bottom on stream.
Yeah, I have to get it to a different. There we go. And it is that one right there. And share. There we go, I think.
There it comes.
Yes. Sorry it took me so long.
Right there at the top of the image, that is a galaxy that we now know has an active supermassive black hole in its center.
That is really, really cool. I think we did see that as a close-up at one point.
What proof do we have that this isn't actually, because to me, are we sure this isn't giant space dragons fighting? Because that's what it looks like.
Well, luckily we can look in other wavelengths of light. And when we look with a different set of eyes, we see, oh, actually what this is 5 galaxies. One of them, by the way, is much closer to us than the other 4. There just happen to be in the same line of sights. That galaxy, if you look at your screen, that looks like a purple firework on your left.
Mm-hmm. Mm-hmm.
That's a closer, nearby, independent spiral galaxy. But the other 4 that you can see, where the little starry spike is, where the 2 little nuclei are underneath it, and then over further to the right, those 4 galaxies are all interacting, actively forming stars, but they're about 7 times farther away than that closer galaxy is.
Oh, wow.
That pink spiky one at the top is just gorgeous. I want to grab it. It's so beautiful.
That's that active black hole.
Oh, yeah.
Look at you falling in love with the black holes like so many before you.
I know. I can't get over them. I am curious, the one on the bottom with the 2 nuclei, what's going on there?
So that is 2 galaxies that are in the process of merging together.
Okay.
Those are 2 galaxies that are in the process of undergoing what we call a galactic merger. Normally, when 2 galaxies meet each other, one of them is much larger than the other one. And that's a nice little process we call galactic cannibalism, because the big one eats the small one, just like you'd expect. But when they're comparably sized like that, what this normally does is it distorts both galaxies. They'll wind up merging together, and a tremendous episode of new star formation will begin. Some of that gas will get kicked out of the galaxies, and you'll wind up with stars and stellar structures that exist in the intergalactic medium for a while. But then in the center, it'll settle down. We used to think that when you get a big spiral and a big spiral and they're comparably sized and they'll merge together, that's how you make an elliptical galaxy. But now we think, yeah, you might make an elliptical galaxy, but most of the time you'll still get another gas-rich disk and still make a spiral. So that's And that's kind of something that we've learned recently over the last 20 years, that's sort of changed our understanding. And this is important for us because we're the second largest galaxy in our own little group of galaxies behind our neighbor Andromeda. And over the next 4 to 7 billion years, the Milky Way and Andromeda are going to merge together. We used to think that that new galaxy that will form in the aftermath of this, which we've already named Milkdromeda, we used to think, oh, that's definitely going to be an elliptical galaxy. And now we think, that's probably going to be a spiral galaxy, and there's a chance that it'll become an elliptical galaxy.
So that was just really cool. I'm so glad that you shared that with us, because those are just beautiful, beautiful depictions and something that we had never seen before, which is just fantastic. That just makes me so happy.
Well, can I move in on a little secret? I haven't announced this yet, but I can announce it to you folks. One of the projects that has just been offered onto my plate, which I've said yes to, is National Geographic and I are going to work together to produce a James Webb Space Telescope book about the first images, how the telescope was made, how it was launched and deployed, and what its capabilities are, and then as many of the wonderful first year of science images and discoveries as we can fit in the book.
Yeah, that beehive design, beautiful.
Mm-hmm.
Oh yeah, the honeycomb segmented mirror. You want to know a fun fact about that gold mirror? You know how much gold it took to make the James Webb Space Telescope?
How much?
There's only 4 grams of gold in that whole thing.
Oh, wow.
Yeah, nothing. Most of those mirrors are beryllium, and then they're coated with a thin layer of gold on top of them. Remarkably, even though it's 6.5 meters compared to Hubble's 2.4 meters, they did such an amazing job with the James Webb Space Telescope that it's actually lighter and less massive than the Hubble Space Telescope. And not by a little either, by like 10,000 kilograms. It's like huge. Like James Webb Space Telescope is enormous and light.
Is the gold is because it's the only material standing up to the heat? Is that why we got to have that gold coating on there?
The gold is spectacular because it's efficient at reflecting infrared light. When you want to reflect visible light, you know, you look at the mirror in your house and that's a silvered mirror. But if you were more interested in infrared light rather than visible light, which maybe you would be if we grew up around a red dwarf star instead of a sun-like star, then you want that gold color. That gold color is going to reflect more of that infrared light than a silver color.
Okay, so I'm going to have another question from the audience, or for the
I was betting someone was going to be mad that I said something bad about Roger Penrose. I'm sorry. I'm sorry to all you Penrose fans out there. It's just
we like to open up all kinds of opinions, so we'll have
never make the mistake that just because you idolize, look up to someone, make them a hero, don't ever let that convince you that they're flawless. A lot of people write to me with things like, well, 100 years ago, Einstein said this. And I'm like, oh, I got bad news for you, buddy. If you're a big fan of Einstein and everything he ever said, Einstein made a bunch of mistakes and was wrong about a bunch of things. And so is everyone. So am I too. Like, you can say, well, Ethan, you said this. I'm like, yeah, well, I used to think this, and so did everyone. And then we saw this thing and we learned it. And I hope that I always have that desire in me, that drive in me to learn the new thing, to refine my knowledge, to change my mind in the face of new information. I think that's a part of correctly doing critical thinking.
Right, absolutely. It's also one of the greatest things about science itself. We're not dogmatic about and you can't be with science. You have to
Well, I
have
mean, you can be, and some scientists are, but science as a whole can't be,
Right.
because
Right.
people are going to come along, you know, and it's the famous, you know, science advances one funeral at a time. Sometimes people thought things are a certain way, and you just have to wait until they stop being around to think that certain way and prevent other people in the field from thinking in this new way. But sometimes changes happen very fast. Everyone was surprised when dark energy was discovered in the late 90s, and within 5 years pretty much everybody had accepted it because the evidence was too good. You couldn't not have dark energy and have a consistent universe.
Mm-hmm. So Kat the Humanist asked, why is the color of things different between the Hubble's pictures and JWST? I think you might have answered that a little bit early on with the one that has the I can't get my words straight. That the JWST.
I know what you want to say, but I'm waiting for you to say it. You can do it, Sonny.
I know. Okay, so the JWST has those cameras that are able to detect the red spectrum much greater.
It can see much farther into the infrared than Hubble can see. But the reason the color of things appears different is because if I were to show you James Webb Space Telescope images as your eyes would see them, that's not what James Webb Space Telescope measures. It's measuring mostly light that you can't see with your eyes. So what we do when you have telescopes like this is we assign colors to them. Some people call it false color. I don't like using the word false color because in that sense, anything is false color. Because what you do is you say, is this what my eyes would see? Well, no. Your eyes are garbage compared to what these telescopes can see. You have like 3 types of cones which see color in your eyes. A telescope like JWST has like 11 different filters in the near infrared portion of the spectrum alone. So what we do is we say, I think there's another 9 or 10 in the MIRI filters too, is we say, look, we're going to take all the light that falls into this wavelength range and we're going to assign red to it. And then we're going to take all the light that falls into this range and we're going to assign green to it, and all the light in this range and we're going to assign blue to it. And then when we combine them together, here's something for your eyes to interpret. So every observatory we have that sees anything outside of the wavelength range that our eyes see, that's useful information. We want to encode that so that you can visually take it in. So we assign colors to different parts of the spectrum. And because Hubble looks at a different wavelength range than James Webb Space Telescope looks at, there's some overlap between James Webb and Hubble. There's some overlap in there where they both get part of the same thing. But James Webb goes much farther this way and Hubble goes a little farther this way, which is why I'm excited that they're both up there at once, because we get these complementary observations where we can see, here's what James Webb sees, here's what Hubble sees, here's what some ground-based telescopes see, that you can get this holistic, what we call a multi-wavelength view of it. Now, still, we have to interpret it so our eyes can see it. So I am a fan of saying, let's make it so that you and me and everyone else can just look at this and say, ooh, this is what it looks like, because that's good stuff. But, you know, let's be honest, it is assigned color. It is assigned color. We're assigning colors to look at it. If James Webb and Hubble were presented in the same colors, they're encoding different information. So I feel like that would be more dishonest to say, oh, this galaxy should look the same in Hubble colors as JWST colors. No, it shouldn't, because you're looking at just a totally different set of wavelengths that's giving you different information about the universe. Remember, light is not just visible light. On the longer wavelength side, past red light, you have infrared, microwave, and radio waves. And on the short wavelength side, bluer than blue light, you have ultraviolet, X-ray, and gamma ray. One of the things we hope for as astronomers is let's get a fleet of high quality observatories that can see what's in the radio, what's in the microwave, infrared, visible, ultraviolet, X-ray, gamma ray. Let's get high quality observatories that span the wavelength. Some of them we can build on the ground. The universe is pretty transparent, or our atmosphere is pretty transparent to visible light and radio light. It's not very transparent to infrared and microwave or ultraviolet, X-ray, and gamma rays. So for those, it's really important to go to space.
Mm-hmm. So I want to change topic just a little bit because there was a couple other questions that I wanted to ask you. However, I just love the JWST. We had an early discussion when it first went out about why the name maybe is not the best, but I love the telescope itself. So I will ask a couple other questions. Is there an edge to the universe, or is it infinite? And if it's infinite, how can it be expanded?
So there's an edge to the observable part. There's an edge to what we can see. And that edge is set by three things. One is the rate of cosmic expansion. Two is the amount of time that's passed since the Big Bang. And three is that finite speed of light, which is how fast signals travel through the universe. We call that edge, what you call an edge, we call this the cosmic horizon. It's as far away as the most distant signals that are arriving now. How far away are they at present? And that answer is about 46.1 billion light years. Now, there's probably, we can't be sure, but I bet you there's more unobservable universe out there beyond that boundary. And we're just waiting for more time to pass so we can see more and more of it. But whether the universe is finite or infinite, it can still be expanding. A lot of people say like, oh, infinity is the biggest thing and nothing can be bigger than infinity. Oh, really? You know, and then people go like, what about infinity plus one? What about infinity plus infinity? What about infinity times infinity? Well, it turns out, yeah, infinite things can grow or shrink. All we can do is measure the part of us, the part of this universe that we have access to. But mathematically, you can have an infinite thing expanding, contracting, evolving, doing pretty much anything that a finite thing can do. The only thing is, we don't know what the ultimate structure of our universe is. Is it truly infinite? Does it go on forever and ever in all directions? Is it finite, like some cosmic four-dimensional donut where it loops back and closes on itself? Is it something where it's huge, like here's our little observable part and the big observable, the unobservable universe goes on, but then there's a boundary where that Big Bang occurred, and outside of that, space is continuing to inflate like it was before our Big Bang occurred where we are? That one, I think, is the most likely because we have the best indirect evidence supporting it. But I don't know for sure. No one does. We can't observe it. You just have to say, here's what we can observe. Here's what's theoretically well motivated. But any of this is still possible. You can't close your mind off to the possibilities just because your theory is limited in its scope at present.
That like makes my brain do like, because it's like.
Let me ask you this. If the universe were infinite, why would you think it couldn't be expanding?
I guess because before you gave that answer, I think it would be because the way that I interpreted infinite is that there is no boundary. Do you know what I'm saying? Like it's
She's
like
talking about
You're
infinite is
thinking
like,
like it's already its
regress.
maximum size.
right. Like there is nothing
But that's
greater than
assuming
infinite.
that there is a maximum size. That's almost like assuming that the universe needs some larger thing than itself to expand into, rather than the universe is all there is and will be and ever was, and is expanding or contracting into itself.
Okay. Okay. So
Because if something is big, even if it's infinite, it can always double or triple in size again. If something is small, it can always halve or quarter or shrink in size again. The universe, you have to recognize, is not like, oh, it's a thing that exists in space and time. The universe is made out of space and time. Space and time is all that there is. It's like the stage on which the play of the universe takes place.
okay.
You're like, well, what if I took the stage away? It's like, oh, honey, you took everything away with it. You took the stage, you took the quantum fields, you took the particles within it. Like, the stage is everything. You take that away, and what do you even have?
So then that makes me wonder about the theory of multiple universes.
Right. So one of the ideas is with multiple universes, and there were two ideas that people conflate together. I don't know what your favorite sci-fi multiverse depiction is, if it's everything everywhere all at once, or if it's more like the Marvel multiverse type of thing. But normally when people in fiction talk about the multiverse, they're talking about it from a quantum mechanical point of view, where they're saying like, okay, look, I recognize that in quantum physics, the universe is fundamentally indeterminate. And there is this set of probabilistic outcomes that can occur. But when I make my critical measurement, only one of them came true. Only one of those outcomes is actually what happened. Now, why? Well, according to standard quantum mechanics, you make your measurement and that picks out which universe are you actually living in, which one of these possibilities describes our universe. But another way to look at it is to say, oh, well, all of these possibilities exist and happen somewhere. And when we make this measurement, it just tells us, oh, and your particular universe is described by this past history, but all of the other universes still go on existing. That's like the quantum mechanics idea of the multiverse. And although there are people who argue persuasively for it, there's no way to say like, oh, well, in my universe, this is what happened, but there is some other universe out there where this other thing happens, and we could somehow communicate. Like, no, you're never going to communicate with, that's not possible. But in inflationary cosmology, there's a totally different type of multiverse that arises that says, look, you have this inflating space, and over here is some rare quantum fluctuation that causes inflation to end. And where inflation ends in this little thing, all of that energy that was inherent to space that was making the universe inflate gets converted into matter and radiation and all of that good stuff that makes a hot Big Bang. So then the hot Big Bang occurs here, and outside of where the hot Big Bang occurs, there's more inflating space, and it continues to inflate and grow and grow. And then again, at some point over here, it's going to have that rare fluctuation, and it's going to end and make another hot Big Bang. So you're going to have lots and lots and lots of Big Bangs that occur in this inflationary multiverse. And that's what we think those two separate definitions of a multiverse are, but people love to mix them together and pretend like they're the same thing. So in the inflationary multiverse, we should have, oh yeah, no, there's a real other universe out there that had a big bang a different amount of time ago than 13.8 billion years, and it's its own expanding universe, maybe even with its own laws of physics, which maybe are the same as ours and maybe are slightly different. We don't know. Because we don't know how inflation ended and what happened with all of that. But they're separated by pockets of inflating space. Whereas the quantum mechanical one just says like, oh, maybe there's a different version out there where I kissed the one who got away at the end of the night,
Yeah.
or where I took this job or this opportunity instead of doing this, or where I a time where I almost fell off that cliff and died. What if I really did fall off that cliff and die in that other universe? Like, sorry, folks. As far as I can tell, this is the only one we got. For
Yeah,
better
I kind of think of that as the philosophical multiverse in a sense, because in philosophy you say, is this possible in all possible universes? So that's how I kind of think that. But
I do want to, before we get jumping too far ahead, I want to say thank you so much to Skeptics and Scoundrels for that $10 donation. No matter how much it might expand or shrink, it'll still be $10. Unfortunately, no, that's fortunately, it'll still be $10. Your $10 is going towards keeping the lights on here at Skeptic Haven. So thank you, and we appreciate your interaction in the live chat.
Yes,
although a price of the light may change.
Yeah, that'll probably be expanding and not shrinking.
Yeah.
So we also have
like
another
my gas budget, right?
Yeah, exactly. We have another one. We have so many great questions from our chat today. Phileas says, did we just ask about emergent versus fundamental space-time? I tend more toward emergent. I'm curious about Ethan's position on that.
So there's sort of multiple schools of thought on this. I try to be agnostic about it. When we talk about the difference between fundamental and emergent, we're talking about the difference between, like, look, if you break the universe down to its basic building blocks, the stuff that you can't break it down any further, this is the fundamental stuff it's made out of. Something's got to be fundamental. And there are a lot of things that are mathematically equivalent. You can say, look, I think in my universe that quantum fields and particles and the space-time they inhabit are fundamental. And that's the orthodox standard view. And then you say, well, what's an emergent thing? And the emergent thing is all the things that are built out of those fundamental things. So atoms are emergent, and human beings are emergent, and entropy is emergent, and all of these other derived quantities that if you went down to a fundamental level and said, well, we've got particles and fields in space-time, and if I take those, I can derive these things from that, thermodynamic quantities and whatnot. Those are the emergent things that come out of it, right? Humans are not fundamental. We're made out of smaller, more fundamental components, right? We're made out of cells, molecules, atoms, subatomic particles. But
I thought you were going to go the four fundamental forces route there for a second there when you started.
Well, that's a possibility. But when people talk about space-time, that's sort of asking, is gravity a fundamental force, or is gravity itself emergent? Well, you can get something that looks like gravity by starting by saying maybe something else is fundamental. Eric Verlinde, for example, has said maybe entropy is fundamental. And if I take entropy as fundamental, I can build and see, oh, I can get something that looks a lot like space-time out of it. Now, it's not quite right because it has like prediction for something that should mimic dark matter, but not quite. That doesn't work out. We know in our universe that if you were to say cosmically, what's the ratio of dark matter to normal matter, and it turns out to be about 5-1. We know that ratio has to be the same at all different cosmic times. And in his theory, that ratio changes over time, that dark matter used to be a lot less important and now it's a lot more important. That doesn't work. But philosophically, it's possible that the things we currently conceive of as fundamental today may in fact be emergent from some simpler set of axioms. I'll just say that from my point of view, we haven't found anything that works that way. We haven't found anything that that says, oh, well, here's something that is really more fundamental than particles and fields or than space and time, and these things that are emergent, they're actually the fundamental things. That's the hard part, is most of the things that we say today are emergent, we know how they arise from the more fundamental things. To say, well, one of these is really fundamental, you'd have to have, well, okay, how is that the fundamental thing? And that's kind of rough. That's kind of rough. So no, I'm not a emergent space-time kind of guy, but you never know. Give me the evidence, I'll change my mind. Until then, I'm working with the best we've got so far.
Somehow I knew you would say something something like that, like give me the evidence and I'll be happy to.
Yeah.
We're getting close to being done, and before we do, I want to highlight one thing that you have in a wonderful thing that has just happened with you.
Oh, the I Made a Thing.
Yes, I made a thing.
Those of you who've heard me on the show before know I have two older books. One is called Beyond the Galaxy, How Humanity Looked Beyond the Milky Way and Discovered the Entire Universe, and Treknology, the Science of Star Trek from Tricorders to Warp Drive. I am so excited to announce that I now have my first children's book available. It is called The Littlest Girl Goes Inside an Atom. And the whole purpose of the book is to learn that science is not about how much you know. It is not about what you can see or what you know or some list of facts you can recite. It's about being curious. It's about that willingness to want to find out about the world and the natural world from the smallest scales to the largest for yourself. And that sense of wonder, that sense of curiosity, that sense of exploration is what is at the core of every scientific endeavor. And I think it's correct to say that children are natural scientists. And what I love about this children's book is it's not only beautifully illustrated and full of very fun rhymes, but at the end of it, we put in a section for adults and parents of curious children that explains to them, hey, if you're the parent of a curious child and you read them this book, you're going to probably get a lot of follow-up questions. And here is some information that's going to help you sating the curiosity of your curious child. So this book is out, and you can find out more and purchase it at thelittlestgirl.com.
I love it. Congratulations on that. I do want to show a super chat really quickly from Dan D from one of the multiple universes. Thank you so much. We really appreciate that. And really quickly, I wanted to ask you, who did the illustrations for your book?
My co-author is Laura Manenti. She is a particle physicist who is originally from Italy. And our illustrator is a woman named Francesca Colanti. And these illustrations are delightful.
They really
and
are.
they really go with the book and help bring it to life. So again, head over to thelittlestgirl.com and check it out. We have some full spreads available to view. I'm pleased to announce that I've just recently recorded the audiobook version of that. So if you don't mind the sound of my voice, you can hear it reading this story to your children or just you, however you like it. But this has been a labor of love, and I think, there are lots of great books out there, children's books about space and astronomy, but there are very few books out there for children that are actually informative and engaging, that are about particle physics and the subatomic world. And so if you check this one out, I hope you love it, and I hope you're a little bit richer for it.
I am excited. If you love the kind of content that we just had here, because, Ethan, I just adore you. I absolutely adore you. You make science and astrophysics fun. So if you want to help promote these type of shows and continue these shows, you can always do the free thing, which is like, subscribe, hit the bell, share, all those good things. That helps us. But I also want to highlight our patrons, because without you, we couldn't do what we do. And our patrons are Sydney Davis Jr., Eric Ozols, Tara S., Ryan, Deneen Murphy, Dan D., Michael Wiseman, Kathy Cotton, Cindy Plaza, myself, Sunny Shell, Aaron Coalson, and Phil Calderone. Thank you guys so much for that.
And don't forget to check out all the other shows on Skeptic Haven with Secular Soapbox on Wednesday. Thursday's The Sunny Spot with me and Sunny. Saturday, we have Global Atheists and Women Atheists Unloaded. And Let's Talk on Sunday is the call-in show. So make sure you check all those out.
We have a lot of fun on that show. I want to highlight that we do have some volunteer positions available. If you would like to help us go behind the scenes or anything else, send us a message on one of our social media platforms. Or you can even say something in chat and we'll get in contact with you. So in the meantime, I want everyone to go out and get Ethan's book. And then remember to think critically. Good night, everybody.